When astronomers point the most powerful space telescope ever built at a star system we think we already understand, we usually expect better details, not a completely new world. But that is exactly what happened around Beta Pictoris, one of the most famous young planetary systems in the sky. Hidden in plain sight, a giant planet was quietly circling its star while generations of observations missed it. This was not just another exoplanet announcement. Beta Pictoris is already one of astronomy's celebrity systems, watched for decades because it is young, nearby, bright, and surrounded by a dramatic disk of dust and debris. Scientists study it as a kind of time machine, a way to glimpse what a newborn planetary system can look like while worlds are still settling into place. The system lies about 63 light-years from Earth, close enough to be a laboratory rather than a distant mystery. It is also only around 23 million years old, which is astonishingly young on cosmic timescales. If our solar system were a middle-aged adult, Beta Pictoris would still be in kindergarten. Astronomers already knew this system had at least two giant planets, Beta Pictoris b and Beta Pictoris c. Those worlds were important because they could actually be directly imaged, a difficult feat in exoplanet science. Usually planets vanish in the glare of their parent stars, but these giants were bright enough and far enough from the star to be teased out of the light. So why was there still room for a surprise? Because even a famous system can hide secrets when the geometry is complicated, the dust is thick, and the planet itself is faint. The newly discovered world, now called Beta Pictoris d, did not stand out as an obvious bright dot in a simple picture. Instead, it revealed itself through chemistry. NASA's James Webb Space Telescope was studying the atmosphere of another known planet in the system when a strange signal appeared in the data. Researchers were not hunting for a third planet, which makes the discovery feel even more cinematic, like a flashlight sweeping across a dark room and finding an unexpected door. The key instrument was Webb's NIR-SPEC, the near-infrared spectrograph. NIR-SPEC can do something extraordinary. It does not just collect light from an object, it spreads that light into a spectrum, separating it into wavelengths the way a prism spreads sunlight into a rainbow. That spectrum acts like a fingerprint, revealing what molecules are present and how the object is moving. In the Beta Pictoris data, scientists expected to see mostly smooth light reflecting off dust. Instead, they found a repeating pattern of peaks and dips, almost like a barcode hidden in the glow. Those features matched carbon monoxide absorption lines, exactly the kind of atmospheric signature you might expect from a giant planet. That matters because spectroscopy can do more than identify gases. It can also measure motion through radial velocity, showing whether the source is moving in a way that makes sense for an orbiting planet. When the team combined the chemistry, the speed, and the location, the conclusion became very hard to escape. This was not a random background star. It was not a brown dwarf lurking far behind the system. It was a real-world orbiting Beta Pictoris, a newly recognized planet embedded inside one of the most studied debris disks in astronomy. And the planet itself is fascinating. The team estimates that Beta Pictoris d is probably at least about twice the mass of Jupiter, making it the smallest of the three known giant planets in the system. Even the smallest giant there is still a monster by Earth standards, a world with enough gravity to dominate its local neighborhood. Its orbit is also revealing. Models suggest it circles roughly 30 astronomical units from the star, a distance comparable to Neptune's region in our own solar system. That places it on the wide side among the known planets in Beta Pictoris, yet still tucked inside the inner edge of the system's dusty debris belt. This is where the story becomes bigger than one planet. Beta Pictoris is not just interesting because it has multiple giant worlds. It is valuable because those worlds are interacting with leftover material from formation, sculpting rings, gaps, and warps in the disk like unseen hands moving through smoke. For years, astronomers have tried to understand the strange architecture of this system. Why is the debris disk tilted in places? Why do certain structures appear sharper or emptier than expected? One possibility is that hidden planets have been shaping the disk all along, and the discovery of Beta Pictoris d adds a fresh piece to that puzzle. In other words, the disk may have been giving away the answer before the planet itself was identified. This happens often in astronomy. We see the fingerprints of gravity first, and only later do we uncover the object responsible. There is also something important about the way this planet was found. Beta Pictoris d was not confirmed by the classic direct imaging approach alone. It emerged from spectroscopic analysis, from noticing that the light itself carried the signature of a planet-sized atmosphere. That technique could become incredibly powerful in the future. Some planets may remain hard to photograph cleanly because dust, glare, or instrument artifacts blur the view. But if their atmospheres stamp recognizable molecular patterns into the data, astronomers may be able to detect hidden worlds that ordinary imaging struggles to isolate. This is one reason the discovery feels like a preview of the next era of exoplanet science. Finding a planet by its chemical fingerprint inside a famous, messy, dusty system hints at a future in which telescopes do not merely take better pictures. They become forensic tools, capable of pulling unseen worlds out of light that once looked like background noise. Follow-up observations strengthen the case. Using Webb's MIRI instrument, the mid-infrared instrument, researchers detected water vapor and methane associated with the new planet. Those molecules helped confirm that the source was not just an odd feature in the debris disk, but a genuine planetary atmosphere. Think about what that means. Webb was powerful enough not only to uncover a hidden giant planet, but to begin identifying the gases surrounding it. We are no longer just counting exoplanets. We are starting to profile them, to ask what they are made of, how hot they may be, and how they fit into the evolution of an entire system. Beta Pictoris has long attracted attention because it resembles a younger version of the environments where planets are born. Around such stars, dust grains collide, clump, and either grow into bodies or shatter into rubble. Giant planets can migrate, stir the disk, fling smaller objects around, and leave behind patterns that last for millions of years. Our own solar system likely passed through similarly chaotic phases. Jupiter and Saturn may have shifted position early in history, changing the flow of material and influencing where rocky planets could form. By watching systems like Beta Pictoris, astronomers can test ideas about our own origins against a living example still in motion. There is another reason this system is a favorite target. Because it is so young, its giant planets are still warm from formation. That leftover heat makes them brighter in infrared light, which gives observatories like Webb a major advantage. Older giant planets cool and fade, becoming much harder to detect directly. Even so, Beta Pictoris d managed to stay hidden. That fact is a useful reminder that famous does not mean finished. Astronomy is full of objects we think we know well, until a new instrument changes the question being asked. Webb keeps doing exactly that. Its great strength is not only its large mirror or its sensitive detectors, but the combination of precision, stability, and wavelength coverage that lets it peel apart complicated scenes. Around Beta Pictoris, that meant separating a real atmospheric signal from the bright confusion of dust, starlight, and instrumental effects. The researchers themselves emphasized caution. Bright blobs in images can fool observers. Dust structures can mimic compact sources, and instruments can create artifacts that look tantalizingly planet-like. That is why the spectrum was so important. A suspicious shape in an image can be dismissed as a glitch, but a coherent molecular signature moving in the right way is a much stronger clue. The discovery of Beta Pictoris d was not a lucky guess. It was a carefully tested interpretation supported by multiple lines of evidence. For people who love the search for life, this planet is not an Earth twin. It is a giant world, probably hot, massive, and not a friendly place for biology as we know it. But discoveries like this still matter deeply to the broader search, because understanding how planetary systems assemble is the foundation for knowing where habitable worlds might ultimately appear. Every giant planet affects the architecture of its system. It can shepherd debris, redirect comets, destabilize smaller orbits, or protect inner planets by scattering dangerous objects away. If we want to know how common Earth-like worlds might be, we also need to understand the giant worlds that shape their neighborhoods. Beta Pictoris d now gives astronomers a richer map of that architecture. With 3 imaged planets in one system, scientists have a rare chance to compare orbital spacing, mass, chemistry, and disk interactions in a single cosmic environment. That is the sort of natural laboratory theorists dream about. And because the system is nearby, it will be observed again and again. Future Webb studies may refine the orbit, estimate the temperature more accurately, and constrain the atmospheric chemistry with greater detail. Other observatories, including giant ground-based telescopes now under construction, could eventually track the system with even sharper resolution. Over time, Beta Pictoris may reveal whether there are still more hidden worlds there. If one planet could remain concealed inside such a well-known system, the possibility of additional surprises cannot be ignored. The disk itself still looks dynamic, layered, and full of clues we have not fully decoded. That is one of the most exciting lessons from this discovery. We often imagine that progress in astronomy comes from going farther out, toward dimmer galaxies and more remote epochs. But sometimes revolution happens close to home, in a star system already pinned to the wall of every exoplanet researcher, waiting for a better instrument to notice what everyone else missed. So the story of Beta Pictoris d is not just about a planet. It is about method. It is about the power of spectroscopy, the value of revisiting famous targets, and the way a new telescope can transform a familiar object into unexplored territory. It is also a reminder that planetary systems are not static diagrams. They are evolving, sculpted places, where gravity and gas and dust are constantly rewriting the scene. What looks tidy in a textbook may be turbulent in reality, and what looks empty may simply be hiding in the wrong wavelength. NASA's Webb Space Telescope was built to study the early universe, galaxies, stars, and exoplanets. Around Beta Pictoris, it demonstrated something especially thrilling, that discovery can happen even when scientists are looking for something else. In a sense, Webb did not just find a planet. It exposed a blind spot in our understanding. And that may be the most important part of all. The universe does not run out of surprises when we build better maps. Better maps simply reveal how much was missing. So the next time you hear that a star system is one of the most studied in the sky, remember Beta Pictoris. One hidden giant world was still orbiting there, leaving traces in chemistry, motion, and dust until the right telescope finally noticed. In the age of Webb, even the familiar cosmos can still ambush us with something new.